Okay, in the first video I defined a Bronsted acid and a Bronsted base and introduced the concept of strong acids versus weak acids. And what I want to do now is basically take us through the ionization equations for the 6 strong acids that I have displayed here on the upper right hand side of my screen. So these are the 6 classic strong acids. I'm often asked in class how you tell the difference between a strong acid and a weak acid, and I have to say it starts with making sure that you know by heart the 6 strong acids that are normally taught in general chem classes or even at the high school level in a regular high school chemistry class. And so the way that you know is by making sure that you know the 6 strong acids. And if you're looking at an acid that's not in this list, then the chances that it's a weak acid are highly probable. All right. Now, what I want to do here is take you through some practice and concerning being able to write the ionization equations and then applying definitions. So although we already did the result for hydrochloric acid, we're going to go ahead and we're going to start with that one again. And so the idea is we're going to take some hydrochloric acid, we're going to add it to liquid water, and we're going to produce a solution. Now the solution is going to contain hydronium ion or proton. All right, and in the last video I defined the fact that the hydronium ion is equivalent to a hydrogen ion as long as we're dealing with an acid that's being dissolved in water. All right, now this is a strong acid, and I want to remind the viewer that what that means is that if I carried out this reaction by taking some concentrated acid, let's say, and I intend to add it to water, and let's say I count out 1,000 molecules of this. Before any reaction happens, there's going to be no hydronium in the solution and no chloride ion. Now, for a strong acid, after the reaction is over, after it's complete, so the HCl is completely reacted with the water, there will be little, if any, actual HCl left in the solution. And instead, we're going to have 1,000 molecules of the H3O plus, and we're going to have 1,000 ions of the Cl minus. All right, that by definition is what makes a strong acid strong by contrast to the situation you have with a weak acid. So down on the bottom right, I'm showing the ionization for acetic acid, which is vinegar. All right, and I'm indicating the same kind of issue here. So before any reaction takes place, so you're gonna make a solution of acetic acid in water. So we pick out 1,000 molecules and we add that to a sample of water. And after the reaction's over, we see that there's still 996 molecules that are in the protonated form. In other words, 996 molecules that still are attached to the hydrogen, whereas there's only 4 molecules of the hydronium produced for 1,000 molecules of the acid that we inputted into the water. So this is the fundamental difference between a strong acid and a weak acid. It's the degree of ionization, the degree of ionization. All right. Now, coming back up here to definitions, the hydrochloric acid in this case is the acid. It's an acid because it is a proton donor, and it is transferring the proton to the water, and that makes the water, since it accepted the proton, the base. And I outlined in the last video how the H3O plus is actually the conjugate acid from the water, right? The base is converted into an acid, and then the chloride is the conjugate base of the hydrochloric acid. So the H3O plus is the conjugate acid of water, which is operating as the base in this reaction, and the chloride is the conjugate base of the hydrochloric acid. The origin of the Cl- comes directly from the acid. So the origin of the conjugate base is coming directly from my acid. Now, let's go ahead. And what I want to do is to impress upon the viewer how this reaction is occurring in a little bit more detail. What we want to do is change the formulas of the compounds into their Lewis formulas. All right, and I've produced a whole number of videos on this issue, so I'm going to go ahead and just transform the molecules directly into their formulas, and you may need to gain some background on this if you're not sure how I'm making these transitions by perhaps watching the playlist of those videos. So I'm going to write the hydrochloric acid this way and the water molecule this way. Now, in the water molecule, the oxygen is more electronegative than the hydrogen. So the fact that, and also because of the way this molecule is shaped, we actually have a partial negative charge that I'm going to draw this way on the oxygen and partial positive charges on the hydrogens. All right, we have a similar relationship on the hydrochloric acid because chlorine is more electronegative than the hydrogen. So both of these molecules, the water and the hydrochloric acid, are two things. They contain polar bonds, and both of these are polar molecules. So this is the relationship we have between the two particles, and you can see how I've drawn this here, lining up the negatively charged, the partially negatively charged oxygen with the partially positive charged hydrogen. And we can use what's called a curved arrow mechanism to show how water, acting as the base, will remove the hydrogen from the hydrochloric acid. All right, and this arrow here just shows that these electrons that are involved in the bond between the Cl and the H are going to remain with the Cl. And this, therefore, once the transition's over with, produces the molecule that's called hydronium, that looks like this with a positive charge on it, and then the chloride. Now, you can draw a similar kind of pattern, and I encourage the viewer to do this for all three of these molecules. All right, and so what I'm going to do is I'm going to move on to the nitric acid. All right, and we can draw a similar ionization equation for HNO3, strong acid with water. All right, ionization equation. We're going to end up producing H3O plus, just like with the HCl, the HBr, and the HI. Only the difference here is the anion that we're producing is a polyanion. All right. Now, similar to the top equation that I just took us through, the HNO3 is our acid. All right. The water is operating as a base. The conjugate acid in this is going to be the H3O plus, and the conjugate base is the nitrate. Now, if we look at the Lewis formulas for these, the nitrate, or excuse me, the nitric acid is going to look like this. All right, and like I explained in the HCl molecule, we're going to have a similar situation here. The oxygen that is bonded to the hydrogen has a partial negative charge on it, and the hydrogen has a partial positive charge. And the water molecule in this case is, again, it's acting as a base. So I'm going to draw it this way so that the little negative partial charge, the pairs of electrons on the oxygen and the water molecule, are faced in towards the hydrogen that's attached to the nitric acid, which has got a partial positive charge on it, and we can use a curved arrow mechanism to show what's going to happen here. And that is how we get, again, to the hydronium, which I'll just draw this way. All right, and a free nitrate polyanion that's now in solution. Now, notice that in each of these cases we have the reaction of a base with the acid. All right, the base, which is water, operating with the acid. In the case of the conjugate base, it's also got basic properties. In other words, it can accept a proton. And what I want to point out here is that the strength of the base water is greater than the strength of the conjugate base that's produced by the acids. So there is a very important point that I'm going to put up here in this spot about strong acids, right, which is a fact. So I'm going to write it as a fact. Strong acids, all right, have weak conjugate bases. Weak conjugate bases. So the base water is stronger than the conjugate bases of the strong acids. All right, now moving on. This next one is sulfuric acid, and as I pointed out in the last video, we call this a polyprotic acid because it's got more than one proton. What's important for the viewer to understand about this is that only loss of the first proton matters for this strong acid. Whoops. No, that's correct. So the second proton is actually not lost, and we end up producing this molecule, which is called hydrogen sulfate. And I'll put an asterisk by this proton. All right, this one, and I'll make a strong statement here. This proton is not lost. It is not lost when H2SO4 is dissolved in water. All right, and then again, this is the acid, the sulfuric acid. Water's operating as the base. Again, this molecule here is our conjugate acid, the hydronium, and the HSO4 minus is my conjugate base, which again, to remind the viewer, is a weaker base than water. Otherwise, this reaction wouldn't happen. All right, and then the last molecule is the perchlorate acid, or excuse me, the perchloric acid. Perchloric acid. All right, and its ionization equation will look like this. All right, and this is the acid, the perchloric acid is the acid, and then the H2O is my base. Again, the H3O plus is the conjugate acid linked to the water. All right, and the ClO4 minus is my conjugate base, and it is linked to the original acid. All right, and I'm going to go ahead and close here.